In this video, we'll be looking at symmetry and assigning point groups. So you want to be able to be given a molecule and be able to assign a specific point group using a flowchart that is similar to this. Now, hopefully by the end of this video, you are able to go through most of these and assign point groups, but it does take a lot of practice to be able to actually assign point groups correctly. In this tutorial, we'll be using two tools. The first one is this right here, which is the flowchart to assign point group symmetry. And the second thing is from a website, and that is this right here. I'll leave the link in the description below. And this is a great site. It has a lot of information about symmetry, and in these animations you can actually play around with a whole library of molecules with different symmetries, and you are able to actually see the different symmetries, the different symmetry operations that are available in these molecules. For now, we'll go back to the drawing board, and we will start with an octahedral complex. So for example, if we have a metal and we have 6 chlorides on it in an octahedral arrangement, and we can also assign numbers to these. So if we have 1, 2, 3, 4, 5, and 6. Now if we take a look from the top of the molecule and we look down, the Cl1 metal and Cl6 behind it, we would see that coming to the right side would be the chlorine number 4, to the left side would be chlorine 2, to the top would be chlorine 5, and down here would be chlorine 6. And so this would be just looking down this axis right here. And so if we take a look at this view, you would be able to tell that if we do a 90-degree rotation, so a rotation by 90 degrees, we would end up with the following arrangement. So we have chlorine 1 in the center, behind it is a metal, and behind that would be chlorine 6. But the only thing changing here is the arrangement of these chlorines. So chlorine 4 would go on top, and then Cl5, Cl2, and Cl6. Now, although the specific chlorines moved, the overall molecule looks the same. And this right here is a symmetry operation. Now, this here is a 90-degree rotation, and if we do that 4 times, we would end up with the exact same atoms in the same location. And this here, what we call a C4 rotation. Now the 4, you can come up with it in 2 ways. One is you take 360-degree full rotation divided by how many degrees you actually do the rotation, in this case 90. So you end up with the 4. Or you can see how far are you rotating out of a full circle. So in this case here, we're only doing a quarter turn, and so that's a C4 rotation. Now you'll realize that we have more than one of these axes that we can have C4 rotation. So if we take a look at the Cl3 metal Cl5 axes, we can also have another C4 rotation. And same idea along the Cl2, Cl4, and with the metal in the center. So we have 3 of those C4 axes, and we will see that coming up with this assignment will be helpful, because in the flowchart, one of the questions asks if you have more than 2 or more of Cn where n is greater than 2. Let's take a look at it real quick. So 2 or more Cn where n is greater than 2. So we have a C4 axis, so that's n is greater than 2, and we do have 2 or more of those. So we know that this compound here would be one of the high symmetry ones. So in this case here, we know it's going to be an octahedral, and we'll come back to that in a minute. Now, for the high symmetry compounds, something like an octahedral, we would have a C4 more than so 2 or more C4 rotations, and if you have 2 or more C5 rotations, then in this case here it would be an icosahedral. And in the case where you have 2 or more C3 symmetry operations available, this here would be a tetrahedral. Now, an example of a tetrahedral would be white phosphorus. In this case here, if we have, for example, white phosphorus, which is a tetrahedral in geometry. And one more note is you want to be able to draw the correct Lewis structure always to be able to assign the correct point group symmetry. So if you don't have the correct structure, you will not be able to have the correct assignment of point group. Now, if you take a look down through the phosphorus here, and we want to see what kind of rotation we have. So if we take a look down the phosphorus in the center, right here, you'll see that coming down from the left would be this phosphorus right here. And going down here would be another phosphorus, and going down here would be another phosphorus. So it's like a pyramid. It is a pyramid with this phosphorus on top and these 3 at the bases. Now these are a 120 degrees apart, and if you do a C3 rotation in this case, so if you rotate by 120 degrees, you end up with the same molecule, the same arrangement. And we have so an axis down here, and we have an axis down this phosphorus, an axis down this phosphorus, and an axis down this phosphorus as well. So in this case here we have 4 of those C3s, and therefore we know it's one of those high symmetry point groups, and it would be a TD, tetrahedral. So first of all, you want to see if the compound is linear. And if the compound is linear, something like carbon monoxide or carbon dioxide, now the difference between the two is the following. So if you have, let's say, carbon monoxide versus carbon dioxide, we'll keep this in mind when we look at the next question. So for the first question, when it asks about linear, so that would be a yes in this case. Does it have an inversion center? So I in this case is an inversion center. So if you have something at plus x, plus y, plus z, do you have the same atom at minus x, minus y, minus z? So in this case here, in the carbon dioxide, it would be a yes in this case. So if you have a dot in the center, anything that is in the plus x, plus y, plus z would have to have the same atom in the minus x, minus y, minus z. So in the case of carbon monoxide, this would not be the case, because if you have a carbon on the left, there will be an oxygen on the right. So in this case here, the one with inversion center would be D infinity H, and then the one with out the inversion would be C infinity V. Now, if the compound is not linear, then you want to take a look and see if it has high symmetry and if it's either octahedral, tetrahedral, or icosahedral. And in this case here, there are different ways you can look at it, but you want to see if you have two or more of these CNs where n is greater than 2, and then from that you can take a look and see if you have a C3, C4, or C5 rotation axes that you're looking at, and from that you can assign these. Now, if you don't have that, let's take a look at an example where we're looking at, for example, BH3. So BH3, if you were to draw the Lewis structure, this would be a trigonal planar compound. Boron has 3 valence electrons, and so this boron would have an empty p orbital as well, and it lies flat on this plane right here. Now we have a 120-degree rotation, in which if we rotate the compound we would end up with the same compound, but we also have other symmetry elements that we will consider as well. So if you take a look at the table here, it asks you if it has any sort of CN rotations. In this case, yes, we have 120-degree rotation, and so this is a C3 rotation axis. And then it asks you if there are any perpendicular rotations, the same number, so C2 rotations perpendicular with the same number as Cn. Meaning, here we have C3. So it's asking you, are there 3 C2s that are perpendicular? Now, we can draw this by looking down the BH bonds and see that, but let's this time take a look at the website and see how BH3 looks like. So we do have a C3 rotation that we mentioned, and in this website, if you actually click rotate, you can actually see how the molecule rotates and ends up in the same arrangement of atoms that you started with. Now, if we're looking at perpendicular, so this here is the principal axis, C3, the highest rotation axis, but we do have other C2s. So in this case here, if you look down the HB bond, you'll see that this hydrogen here, if you were to rotate by 180 degrees, this hydrogen on the right goes to the left, and the hydrogen on the left goes to the right, while the atoms in the middle stay put. So in this case here, let's take a look at the rotation. So if we rotate around the C2 axis here, whatever's in the axes would stay put, and whatever's outside the axis would do a 180-degree rotation. So we have one along this HB bond, and then we have another one along this HB bond, and then we have a third one along the last HB bond. So we have a C3 rotation axis, and then we have 1, 2, and 3 perpendicular C2s. So in this case here, if we take a look at the flow chart, so we would have 3 C2s that are perpendicular to the C3 axes. So we know that it has to be part of the D family. Now we would have to assign which D point group it is, but we would at least know that it starts with a D for now. Next, it asks you if there are any perpendicular mirror planes. So sigma h, just as this case here, sigma h is any mirror plane that is perpendicular to the principal axes. So you take that C3 axis, and that what is perpendicular to this would be along the 3 atoms. So all these atoms would be in the perpendicular plane. And so if you were to do a sigma h symmetry plane, which is the mirror plane along all of these atoms, they would stay put, because anything that is above that plane would go below the plane, anything that is below the plane would go above. But if something is within the plane, it stays the same and it stays put. Therefore, we know that the assignment in this case for BH3 would be D3H. So in this case here, this here is D3H. Now, let's take a look at water, for example. So what if we have a water molecule? Okay, so we have water here. Now, let's do the same thing and follow the chart. So first of all, we know that this is not linear compound. And if we were to look around, we would find there's a C2 axis here. If you rotate this by 180 degrees, you end up with the same compound and arrangement. Therefore, we do have at least a C2. Now, in terms of perpendicular C2s, so do we have two C2s that are perpendicular? So let's take a look here at the compound. So if we look perpendicular, if we were to do a rotation by a C2, so 180 degrees, we would end up with the hydrogens pointing up. So 180 degrees, this hydrogen would go down here, this hydrogen would go to the other side here, something like this. And so it's not the same anymore. It's not the same arrangement in space. So let's go back to the point group chart. So in this case here, it's a no. So we know it's from the C family. And then it's asking if it has a mirror plane that is perpendicular to the principal axis. We said the principal axis in this case is C2. So that's the principal axis, and perpendicular to that would be this here. So if you were to have a mirror plane, those hydrogens that are pointing downwards would point upwards, and this compound would not be the same anymore. Okay, so we'll go to the next step right here. So in this case here, it's a no for sigma H. What about sigma V? It says N sigma V. So do we have two sigma V's that are along the principal axes? So in this case here, we do have a mirror plane. If we cut this molecule in half, whatever's on the right is the same as whatever's on the left. So that's a mirror plane along the principal axes. And then we have a second mirror plane just 180 degrees away from that. And in this case here, we do have two sigma V's that are along the principal axes, C2. So if we go back to the flow chart, it's a yes here, so this would be assigned as C2V, since N represents the principal axis of rotation. So lastly, let's take a look at some of the cases where you do not have any linear or high symmetry or even any kind of rotation. So in this case here we have 3 cases. Let's take a look at the website. So we have the case where we have So CS. So CS means that there is a mirror plane in the compound. There's no rotation, but there is a mirror plane. So if we take a look here, there is no way you can rotate this compound. So if you rotate here by 180 degrees, the bromine would go in the place of the chlorine would go in the place of the bromine, so it's not the same compound anymore. But if you look down here, we do have a mirror plane. Whatever is on the right is the same as on the left, because whatever is in the plane of the mirror plane stays the same. So this right here would be the mirror plane that you're looking at. So although it doesn't have any CN rotations, we do have a mirror plane cutting through the molecule, and so the assignment in this case here would be CS. Now there are cases where you don't have CN or even sigma H, and an example of that would be this compound here. So in this compound here, we do not have any rotation. So if you rotate by 180 degrees, this bromine goes here, but the bromine on the other side is downwards. It's connected to the other carbon. It's not the same. And we do not have any mirror plane. So if we look down through here, you have a bromine across from a chlorine. If you look down here, the hydrogen's on top here, the hydrogen is on the bottom. But what we do have is an inversion center. Whatever is on the, let's say, plus x plus y plus z would be on the minus x minus y minus z. So if something is on the right top, front would be on the rear back left. And same idea. So this here is up and to the left, and this hydrogen is bottom and to the right. So there is an inversion center. So if you invert, you'll see that there is whatever is on plus x plus y plus z, there exists another atom that is the same on minus x minus y minus z. So in this case here, we do have an inversion center, so this would be a Ci. Now, if you do not have any inversion center or any mirror plane, something like if we have a carbon here with a hydrogen, and we have a chlorine, a bromine, and a fluorine. So in this case here, we do not have any mirror planes, no inversion centers, no rotation axes, and therefore we do not have any identity except E, which is the molecule by itself. And in this case here, the assignment would be C1 for this compound. So hopefully by the end of this video, you are able to look at this flowchart or similar ones and be able to follow along answering questions about the given molecule that you're looking at, and be able to come up with a point group assignment at the end. Now, in future tutorials, you'll see that figuring out the point group assignment is important, because we will be dealing with what we call character tables, and from those we will get an insight about the bonding nature of the compound, as well as different vibration modes within that compound.